All right, this is Monsieur again, continuing to look at the optics unit. This one we're going to review the main terms to describe an image and how we can look at this from a number perspective in terms of also what you're going to be looking for when we do ray diagrams. We're going to look at the two types of mirrors, and then I'm going to try to illustrate how to draw out a ray diagram, the steps for drawing a ray diagram. Then there'll be another video where I essentially go through and draw all the different types of ray diagrams for mirrors. So here we go. So for this one, let's go over the ways to describe an image. Okay, when I want to describe an image, all right, we went over 4 ways from the prior video. Okay, first one, is the image real or virtual? Okay. Now again, this might not make complete sense yet, but I'm going to jump straight into it. Okay. A real image will always have a positive image distance, denoted DI. Okay. A real image will always have a positive image distance when we calculate it. Virtual will always have a negative image distance. All right. That's from a mathematical perspective. From looking at the ray diagram, a real image will always be created by real reflected light. A virtual image will always be created by sight lines. Okay, so that's going to be one of the first things. Okay, 2. The second one, I'm going to actually, I know I went in a different order. I'm going to go with, is the image enlarged, diminished, or same size? Now that's going to be related to the magnification of the image. Okay? And so magnification, as you know, basically is telling you, is the image getting larger, smaller, or staying the same size? All right. The magnification, which will be denoted M, all right. Basically, we know it's going to be enlarged if the magnification is greater than 1. All right. Basically saying you are, multiplying the size of the image by the magnification. That's what we're looking at here. So if it's greater than 1, that it means it's larger. If the magnification is less than 1, all right, that means it's smaller. And if the magnification equals 1, that means it does not change size. The image and the object are the same height. Now I need to go back. There's one thing you need to do. This is the absolute value of the magnification. All right, because we're going to see in a moment we can get a positive and negative magnification, but we have to ignore that sign. All right, it's the number. That's what we're focusing on. Is the number for the magnification greater than 1 or less than 1? In other words, a decimal. We don't go less than 0. If it's 0, that means there is no image there. But the thing is, you will see, we will do problems where it's -1, -2, and -3. That is related to the third description of an image, whether the image is upright or inverted. Now there's actually 2 ways to figure this one out. Oh, going back to number 2. How can I see this by drawing it? The arrow is going to look larger or smaller or a similar size. So that's pretty self-explanatory. Basically look at the image and object arrows. All right. Now, if it's upright or inverted, there's 2 ways to figure it out. If it's upright, it'll either be a positive, well actually it's going to be both of these things. It will have a positive magnification and it will have a positive image height. All right, these are all things we're going to calculate. Magnification, image height, distance height, I'll show you how. All right. Inverted, you're going to have a negative magnification, which means you're going to have a negative image height. All right, and I'll do a couple examples to make sure we understand this. Oh, I put distance height, this image distance. image height. Okay? So upright or inverted, positive m, positive h, negative m, negative h. Okay? Negative hi. All right? That's what we're looking for. Again, pretty clear on your drawing, the arrow will be upside down. The one arrow will be up, one arrow will be down if it's inverted. If it's upright, both arrows will be going up. All right? The last thing that we were talking about here is where is it? Where is the image? That's obviously going to be related to image distance. All right? So that'll be pretty clear. We'll go over that one much more specifically when we start drawing out our array diagrams. Okay? So, if I do a quick example here. So I'm going to skip a couple things. Okay? If I said magnification equaled positive 2.6. The magnification was positive 2.6, and there's no units for magnification. We'll go over that again as well. All right? That means you know two things about the image. One, you look at the positive sign and the number separately. 2.6, that's greater than 1. That means this image has to be enlarged. Positive, that means the image has to be upright. So you're going to have an image that is upright and enlarged. That's all you can tell me based on the magnification. You cannot tell me whether it's real or virtual or where is it. You have no idea. All right? What if you had a magnification of negative 3.0? This is usually one that people from, starting this out will mess up. Okay? They'll go, all right, we have to look at these separately. What a lot of people tell me is they go, negative 3, that's less than 1, therefore it is diminished. That is incorrect. The negative and the number are separate from each other. They're giving me separate information. The negative sign is telling me that the image is going to be inverted. The number, which is greater than 1, means the image must be enlarged. So this is an inverted, enlarged image. So when do I get diminished? That would be where you have something like this, a magnification of positive 0.25. This is upright. This is diminished. Okay? So it's all about the number and the sign separate from each other. All right? So we got to be very careful with that. Again, we'll get to the specific calculation a little bit later. All right. There are going to be two types of mirrors we're going to be using. We have a concave mirror, and we're going to have a convex mirror. A concave mirror. Okay? What happens to the concave mirror is all light rays will reflect back through a particular point. And the particular point is called a focal point, which will denote F, capital F. Okay? A focal point. All right? So these light rays, if they're drawn in perfectly parallel, they'll reflect back. Sorry, it's not perfect. They'll all reflect back in and toward the focal point, which is in front of the mirror in this particular case, F. If it comes in below, based on the curvature of the mirror, it will reflect up. Okay? So that is a concave mirror focuses all the light in front of the mirror itself at its focal point. A convex mirror bends out, which means its focal point is on the opposite side of the mirror from where the light is coming. So the light comes in. The focal point's on the opposite side because it's helping us determine the angle of reflection for all of those light rays. Obviously, as it gets closer to straight on with the focal line, it doesn't reflect as steeply. Okay? If it comes in below, it reflects back down that way. Obviously, for both concave and convex, if it travels right through the focal point, right in the center of the mirror, it'll reflect straight back. That is definitely true. All right? So this is where we're going to run into issues of, hopefully we'll not run into issues, but make more sense of real light versus sight lines. What I'm drawing over here, these are the sight lines. Basically how your eyes, your brain, focuses that light on the opposite side of the mirror and hopefully creates an image out of it. All right. So that also introduced a new term called the focal point. The focal point is the point where all light converges. Okay? Even with the convex mirror, technically those sight lines are all converging on the opposite side of the mirror. In relation to that, that's capital F when we start drawing these diagrams. We have lowercase f. This is known as the focal length. The focal length. All right? It'll be measured in centimeters just like the image distances are and things like that. All right? So those are our two types of mirrors. Convex diverges the light. Sometimes we would call this a diverging mirror. And this one a converging mirror. Okay. It diverges the light, it converges the light. All right, so the last thing to talk about today is this crazy image. All right, I'm going to try to help you out here and try to focus this down some. Get rid of some of these lines up top here. All right, yep, we're going to go with that. So, a ray diagram, okay, has a few very important points we need to always draw into that. Okay, I'm going to go a new page and basically illustrate what we're going to do here. We're going to be drawing out essentially a graph. Okay, it'll look like basically like this, a two axes. All right, the y-axis is going to be where your mirror or lenses. You don't even have to draw it in. Sometimes we like to, just to kind of illustrate very clearly what everything should do. But the y-axis acts as where your mirror or lens is. All right. Like I said, if I do a concave mirror, I might draw that in just so I see how the light rays should bounce back. The thing is, all light rays are going to come in and go all the way to the y-axis before reflecting back. Don't stop. Don't stop right here. All right, go all the way to the y-axis. The y-axis is your mirror, even if it's curved or whatever. If you don't do that, it's going to make it obviously a lot more difficult to do everything correctly. Okay, so the y-axis is your mirror. The x-axis is basically the space that you are going to place your object on. So, I'm going to place my object out here. I'll do a little arrow and draw O, object. All right. Now, the thing is, there's quite a few measurements you need to make sure you're doing very, very carefully. All right? And that's where I'm going to go back to the prior page. On the prior page, you saw we had 2 points that we really, really need. One is little f, and one is c. Okay? C and f. So, we already talked about f. Okay? This would be f right here. You can do it capital F too, that's fine. All right? That is your focal point. That's where all the light is going to converge back toward. All right? The distance between the focal length, the focal point, and the mirror is called the focal length. It is the distance between the focal point and the mirror. All right? Don't worry about my calculations yet down there. The other important point is called the principal axis. We just call it that. That's sometimes where it gets confusing because people call this whole horizontal line, the x-axis, the principal axis. But the principal axis is specifically the radius of the mirror. And again, a lot of this stuff is very confusing because you're going, radius of a mirror? It's what would happen if this mirror technically extended all the way down and around like a circle. Okay, this mirror right here that I have half drawn. All right. Where would the center of that mirror be? That is denoted C, so that's nice. C stands for principal axis, all right? And so it is you can say the radius of the mirror, that's fine, but we denote it as C. And so principal axis is the distance from the center all the way to the mirror edge itself. Now the nice thing is, the focal length and the principal axis are very closely related. The focal length is equal to half the principal axis, always. I have r over 2 here too, in case you keep on going, wait, what's the principal axis? It's the radius, all right? Now again, we're not going to draw a complete circle ever. These problems will be very specific. I mean, I'll go to the next page and show you. A 5 centimeter object is placed 22 centimeters from the concave mirror with a focal length of 10 centimeters. They will give you all of these distances, all right, in terms of what's going on, all right? And that's what we have to use. If I have the focal length, I have the principal axis length. If I have the principal axis length, I have the focal length. The focal length is half of the principal axis. That's what we need to know. All right? So, that is basically finally the rest of the terms we have here. All right? Principal axis, focal point, focal length. All right? That finally leads us to being able to start drawing what are called our ray diagrams, which is going to be the majority of your tests, which is going to be the majority of your assignments, is drawing out a lot of these. All right? So, when you're doing a ray diagram, okay, when you do a ray diagram, first, I believe I have a file that already has these drawn out and measured correctly. You do actually have to measure these out correctly. If you don't, the drawing does not come out right. We have to be accurate with our measurements. The distance from where the mirror is to the focal length, the principal axis has to be double that. So if this is at 10 centimeters, the principal axis must be at 20 centimeters. You just have to do it to scale, so it doesn't have to be exactly related to it. Like I know it says 10 centimeters for the focal length. You can draw that. But again, if you're talking about a piece of paper, it's going to be really tough to always draw every single focal length exactly as the problem is giving. Scale it, all right? So like for instance, on mine, I believe this is probably like 20 centimeters long, and then this is 40 centimeters long. It's the same thing, 10 to 20. It's the same ratio. So as long as you get that ratio, that scale right, you're okay. So when you draw these out, and it says you have a 5 centimeter object is placed 22 centimeters from a concave mirror with focal length of 10 centimeters. Basically, my question is going to be, draw the image and describe. Draw the image and describe. All right? And so, what that means is, we need to draw these out very, very accurately. This is part of your test. You will be asked to draw these out, and they have to be accurate. All right? So the first thing you do is you draw out your ray diagram situation. You draw where your object is. You draw your mirror. You label your principal axis and your focal point. So you draw out your x and y axis. You measure a certain distance to the focal point. You measure then you double it, and you go to the principal axis. Usually on a piece of paper, I measure 4 centimeters and then 8 centimeters. I don't know why I picked those two numbers. A lot of people do 5 and 10. All right? And it doesn't matter what the measurements are, that scales it for you because you know it's going to be related to that. You have to draw in your object. Your object is always we always work from the left side of the mirror. Okay? Always on the left side. You can do the right, but you're going to see I will only do ones from the left. All right? So I draw in my object over here. This 5 centimeters, that's the object height. So that's my object height. It says the object is placed 22 centimeters from the focal length. So that's my object distance, 22 centimeters. All right? And it has a focal length f of 10 centimeters. So again, that's why I know that means C is 20 centimeters. That is how I know where to place my arrow. My object is greater than C, so it's even farther away from the mirror than C. So that is what I first initially draw. Excuse me. All right? And I always draw my object up. Don't ever draw it going down, going straight up. All right? I would recommend generally drawing it pretty small. It does not have the object height. That is not that important. Draw it so you can fit your answer. Okay? So draw the diagram out, and you'll see me do this over and over and over again. What you then have to do is you have to draw two light rays to figure out where the image is. It involves two light rays. Ray number one, called the parallel ray, is going to be drawn from the top of the object to draw from the top of the object parallel with the axis and reflect it back through the focal point. So I'm going to use the prior page to try to illustrate this. All right. I'm going to have to erase some things here. So the parallel, and I always like to use an arrow. What we do is that the light ray travels parallel with the principal axis straight to the mirror. Okay? Straight to the mirror. It then will reflect back through the focal point, just like this. And you can see, you want to be exact. You want to make sure you're going right through the center of your focal point. And if you don't measure it out right, your image is not going to appear in the right spot. All right? You can draw the line. So this is the first ray. This is called the parallel ray. It's drawn parallel into the mirror and straight back through the focal length. This is going to happen every time. All right? Every time. So that's the parallel ray. Ray 2 is called the focal ray because you basically do the opposite. You could draw from the top of the object through the focal point and then reflect it parallel back with the axis. So what that means is this. I still start at the top, but this time I go through the focal point down to the mirror. When I hit the mirror, what's that light ray going to do? It's going to reflect straight back. Reflect straight back. All right? So I get this image, and this kind of drawing. This is going to be very common. All right? Well, what do? I drew these two lines. I went one in and back to the focal point, one through the focal point, and straight back. What do I do next? Where is my image? I said I only need two rays. Well, it turns out the point of intersection between the two rays is the top of the image. The two, I'm going to be more specific here, reflected rays. The reflected rays is where the top of the image is. So, because I'm doing two light rays from the top of the image, the two reflected rays are telling me where the top of the image is. Sorry. Since I'm doing two light rays on top of the object, it's where the top of the image is. Technically, you can do these two light rays anywhere on your object, and that will tell you where that section of your object is, where that image piece is on the other side. But we always work from the top. And so what we get here is this is where the top of the image is. So then I can just extend the image back to the principal axis. So in this case, this is the top of the arrow. That's why I'm drawing it down, because that's the top of the arrow. And then I extend it back to the x-axis. This is my image. All right? That is my image. All right? And again, you're going to see, I'm going to do 5 more of these, so you'll get the hang of what we're trying to do with this. This is just the initial, what do we do to draw ray diagrams, and then what do we do to figure out and draw for the image. Okay? So then if I do this pretty quickly, based on all of this, I can now describe my image. All right? As long, again, all my measurements are good. This is a good spot. This is where I'm expecting my image, knowing how to do these. All right, let's describe this image. All right, and some of this might be a little tough because you might be going, well, I can't tell, but that's okay. We'll go over in more detail on another video. First off, you can clearly tell my image is going to be inverted. My image is inverted. All right. If I look at my image, basically at the height of them, it is actually going to be a little bit diminished. the image is actually smaller than the object. All right. I don't know if you can see that or not. Some of you might think it just looks the same size, but it is actually smaller. Okay. It's diminished. This is going to be a real image. This is going to be a real image because these are real light rays. The light reflects back. It's created by two real reflected light rays. It's real. The other reason, knowing this, is on a mirror. Anything to the left of the mirror, of the y-axis, is considered positive image distance. All right? We say it's positive because that's the direction the light's actually going. Anything on the opposite side of the mirror is considered negative image distance. So that's the other thing. This is going to be a positive image distance, and therefore it's on this side. That's real. The last thing, this is one we haven't gone over. How do I describe where my object is? Well, the way I describe it is where my image is. Is it beyond C? Is it past here? Past C, up here? No. Is it at C? No. Is it between C and F? Yes. So I would say it is between C and F. And I can confirm that by finding the image distance. It's going to come out between 10 and 20 when we start actually doing calculations for it. The other areas, at F, before F, or we just say on the opposite side of the mirror itself. Negative DI is what we'll usually say. Okay? So that's what we mean by where is the image. All right? So, again, I know a lot of stuff, a lot of things we went over, a lot of new terms. Okay? The idea of the how to describe from a numerical value, which again we haven't gotten into that just yet, but also by looking at the diagram, how to figure out real or virtual, enlarged or diminished, upright or inverted, and then where is it? Concave mirrors converge that light at a focal point before the mirror. Convex focus the light beyond the mirror, behind the mirror. Okay? And this was an initial example of a concave mirror problem. We got the principal axis, that's the center of the mirror. It has a distance 2 times that of the focal length from the mirror. So the focal length is half of the principal axis. All right. And then finally, we drew one diagram out. We're going to draw a lot more in the next video. This one is just showing you we have 2 rays always. It's always going to be 2 rays. One that goes straight in and then comes back to the focal point. One that goes diagonally to the focal point first and then straight back. You'll see a pattern. All right, that's what we're looking for. So that is it. Thank you.